In the world of modern software development, the mantra is move fast and break things. We push updates on Fridays, we fix bugs in production, and we accept that our apps will crash occasionally. It's annoying, but nobody dies if Instagram goes down for 10 minutes. But there is a place where software cannot crash. A place where a blue screen of death means actual death. A place where a single bug can vaporize billions of dollars and end human lives. That place is NASA. When you are writing code for a spacecraft hurtling towards Mars at 20,000 miles per hour, or for a rover landing on a desolate planet millions of kilometers away, you don't get a second chance. You can't just SSH into the rover and restart the server. The latency is 20 minutes. By the time you realize something is wrong, the rover has already crashed. This extreme environment has forced NASA to develop a coding philosophy that is the complete opposite of Silicon Valley. It is slow. It is methodical. It is paranoid. They don't use the latest frameworks. They don't use JavaScript. They don't use Python for critical systems. They use C, but not just any C. They use a restricted, stripped-down version of C that adheres to a set of rules so strict they would make a normal developer cry. These are known as the Power of 10 Rules, created by Gerard Holzman at NASA's Jet Propulsion Laboratory, JP. To understand why NASA codes the way they do, we have to look at the constraints. Space is hostile. Radiation flips bits in memory. Cosmic rays can turn a 0 into a 1 without warning. The hardware is ancient by modern standards because it has to be radiation hardened. The processor on the Perseverance rover is roughly equivalent to a glorious Macintosh from 1998. And memory is scarce. You have a few megabytes, not gigabytes. So the code must be incredibly efficient, incredibly stable, and incredibly predictable. Rule number 1 of NASA's philosophy: no dynamic memory allocation. This means no malloc, no free, no garbage collection. In a normal program, if you need to store a list of users, you ask the computer for memory as you need it. If the list grows, you ask for more. But dynamic memory is dangerous. It leads to memory leaks. It leads to fragmentation, where the memory is like a Swiss cheese full of holes, and suddenly you can't find a contiguous block to store data. If that happens in space, the system crashes. So NASA allocates everything up front. If the software needs memory, it grabs it all when it boots up. If it huns ouchie, it doesn't crash. It just stops accepting new data in a controlled way. It's like packing your suitcase for a trip and welding it shut. You can't add anything later, but you also can't lose anything. Rule number 2, no recursion. Recursion is a beautiful concept in computer science where a function calls itself. It's elegant for solving mathematical problems. But it's a nightmare for safety. Each time a function calls itself, it uses a bit of stacked memory. If it calls itself too many times infinite recursion, you get a Stack Overflow the error, not the website. The computer runs out of space and dies. NASA forbids this. They use simple loops. Loops have a fixed upper bound. You know exactly how many times it will run. You can mathematically prove that the loop will terminate. You cannot prove that for recursion. This brings us to the concept of static analysis. NASA doesn't just run the code to see if it works. They use mathematical tools to read the code and prove it is correct. They treat code like a mathematical equation. Tools scan every line, looking for potential divide by zero errors, potential buffer overflows, potential logic traps. If the tool finds even a 0.01% chance of a bug, the code is rejected. They aim for 0 defects. A commercial operating system like Windows or Mac OS has thousands of known bugs. The software on the space shuttle had something like 1 bug per 400,000 lines of code. It is a level of perfection that is insanely expensive but absolutely necessary. Before we dive deeper into how they handle cosmic radiation flipping bits in your RAM, if you find this kind of deep technical analysis fascinating, make sure you are subscribed. We don't just look at the surface of tech. We look at the engine room. And leave a comment below. Would you survive as a developer at NASA with these rules, or would you go crazy without your dynamic arrays. Let's talk about the watchdog timer. This is the ultimate failsafe. Imagine a timer counting down from 10 to 0. Another fascinating aspect is the human side of this. Code reviews at NASA are not like code reviews at a startup. They are interrogations. You sit in a room and your peers tear your code apart line by line. You have to justify every variable, every condition, every comment. It is ego, but it removes the bus factor. If only one person understands a piece of code and that person gets hit by a bus or leaves the agency, the project is at risk. At NASA, the code belongs to everyone. It is written to be read by humans first and computers second. Clarity is valued over cleverness. A clever one-liner that saves 3 bytes but is hard to understand is rejected. They prefer boring code. Boring code is safe code. The navigation software is another beast entirely. It involves orbital mechanics, relativity, and physics. The Voyager probes, launched in the 70s, are still running code written in Fortran and assembly. These probes are billions of kilometers away, leaving the solar system. NASA engineers recently had to patch Voyager from Earth. Imagine debugging a system with 40 years of legacy code, where the original developers are retired or dead, and the round-trip time for a signal is almost 2 days. You send a patch, and you wait 2 days to see if you bricked the spacecraft. That requires nerves of steel. But perhaps the most surprising thing is that NASA is starting to change. With the rise of SpaceX and the commercial space industry, there is pressure to move faster. SpaceX uses C++. They use Linux. They use more modern hardware. They accept a slightly higher risk profile because they can launch rockets cheaper and faster. NASA is adapting. They are using more open-source software, like the Linux helicopter on Mars, Ingenuity. They are using Python for data analysis on the ground. But for the Class A safety-critical software, the stuff that keeps astronauts alive, the old rules still apply. The power of 10 is still the law. Why does this matter to you, a developer, writing a web app or a mobile game? Because we have lost the art of efficiency. We rely on fast hardware to mask our sloppy code. We import massive libraries to do simple tasks. We let memory leak because we have 32 gigabytes of RAM. Who cares? But this bloat has a cost. It costs battery life. It costs server bills. It costs user experience. Learning how NASA writes code teaches us discipline. It teaches us to think about edge cases. What happens if the network drops? What happens if the disk is full? What happens if the user inputs a negative number? NASA handles these cases because they have to. We should handle them because it makes us better engineers. There is a beauty in constraints. When you can't just npm install your way out of a problem, you have to actually solve it. You have to understand the machine. The code running on the Curiosity rover is a masterpiece, not because of what it does, but because of what it doesn't do. It doesn't waste. It doesn't guess. It doesn't hope. It executes, so the next time your app crashes because of an unhandled exception, or your browser eats 4 gigabytes of RAM to show a text page, think about the code running on Mars right now. Think about the engineers who wrote it, knowing they would never be able to touch the hardware again. That is the standard. That is the benchmark. We might not all be rocket scientists, but we can all learn to code with a little more gravity. If you enjoyed this journey into the extreme engineering of spaceflight, hit that like button. It helps us navigate the YouTube algorithm. And if you want to learn the skills that build resilient, secure, and powerful systems, maybe not for Mars, but for the real world, check out the channel's playlists. We dive deep into the protocols and languages that actually matter. Stay curious, stay disciplined, and keep your code safe.